do just fine with this. So I'm gonna go back and forth, and you can pass, but let's see what we got. So the first one kind of sets the stage that we know this, we have this rate law expression, have two reactants, second order A, first order B. And so the way this works then is, and I'll start with you, Allison, what if we double this? What will happen to the rate?
It's already has the exponent too.
So what?
What do you mean? Like,
Yeah, so no, I'm doubling, like the molar concentration A, I'm taking it and I'm ramping, I'm taking it twice as much. And then, so what? The rate will have to change, and how will the rate change?
it would probably increase.
Increase by how much?
4.
By 4. Yes, that was what I was after. Yep. The concentration is of A is doubled, your rate will be 4 times. Very good.
And that's because it's
Second order. Yep. And actually, we did by inspection, remember, way back, seems like forever ago. Just by inspection, if you double the concentration and you see a 4-fold increase in the rate, you know that it must be second order. Okay, this one's to you, Daniel. What if you take B and you take half? What will happen to the rate?
it's definitely going to decrease, right?
Right? Decrease?
By half.
Yeah. I'm just, yep, it will go down by 1/2. Very good. Yep, you got it. Okay, back to you, Allison. Okay, so what if we're going to do both of those? We're going to double A, and then we're going to have B. What do you think? We'll go up or down.
It'll go up still,
Mm-hmm.
but maybe like 2 times?
That's what I'm thinking. Go up by a factor of 2. Yep.
And so, just because it's like a review, my thought process for that, right, would be that if the concentration rate is doubled, that's 4 times, and then the other one makes it half, so then it's just like take half full.
Yep. Yep. These may have nothing to do with what you're going to see in your test on tomorrow, but it's supposed to get you thinking. It may or may not. Okay, so here we have this gas phase reaction. And somebody told us that the rate law expression is rate law constant times molar concentration of each of the reactants raised to the first power. So they're first order, right? Okay, so that's not a question yet. So we left off with you, Daniel. Okay, so are these, you got a 50-50 chance, true or false? Okay, so again, here's the overall reaction of interest. Here's the observed rate law expression. So is it true or false that this reaction must occur in a single step? True or false?
Is it true?
And why?
It's first order overall. But I really don't know.
Okay, yeah, this was the lecture that you missed.
Oh, okay.
So actually it is false.
Is it
It doesn't have to occur. It can occur, and this is what you were going to say. It can occur. Up here, where I put the reaction mechanism, I had these different steps. If it occurs in just one elementary step, these things I wrote down were the elementary steps. If it occurs in just one elementary step, we call that an elementary reaction. And then we can use molecularity to go right to the rate law expression. Any questions? So the answer's false.
So the answer is false because what? What is it?
The answer, it might. The answer's false because it says it must, and it does not have to, but it might. It might not. If the word was change, this reaction might occur in a single step, I'd say true.
And you can determine that by looking at the rate law expression.
If it says, no. I don't know if I know.
So what would, wait, so you have to like kind of break it down, right?
Right,
So there's no way to know from like just looking at
right.
it. Okay.
Yeah, the mechanism isn't given. Yeah. You done, Cole?
Yes.
Hopefully I'll stop calling you Caleb.
Yeah, it's all right.
Thank you, sir.
No problem.
Okay. All right, so on to you, Allison. This is a second order reaction overall, true or false?
Let's say false,
And why?
because there's no superscript, so it'd be like 0.
Nope, if there's no superscript, that's for first.
I mean 1. But there's 2. So false.
Okay.
So I mean it's true.
Actually, this is true because remember how we get the overall reaction order is we add m plus n. So 1 plus 1 is equal to 2. Yep.
So what if you got like 2 plus 1?
Be third reaction. Yeah, overall
We
third.
didn't, like, really cover anything.
No, but we did enough to know that units of K are going to have to adjust based upon the overall reaction order. Yeah. Yep. Yep. So we good. So yeah, it is true. Okay, back to you. That's why we review, right?
Yeah.
Okay, so back to you, Daniel. Will raising the temperature cause the value of K to decrease? True or false? Increasing the temperature.
Well, I do know that raising the temperature makes the whole reaction go faster.
So if the reaction goes faster, is K going to go down? False. Yeah. Increasing the temperature actually will cause the value of K to increase. So this is false. This is a false statement. And kind of remember behind the scenes, and I'm going to grab, I made sure it looks just like this. You guys are so spoiled. It'll look just like this. So down here we have the Arrhenius equation that says the rate law constant K is equal to K0 Arrhenius constant E raised to the negative EA over RT. And there's actually kind of behind the scenes where temperature is kind of affecting your K mathematically. Okay. All right. What else we got? So back to you, Allison. Raising the temperature lowers the activation energy for this reaction. And again, if you just kind of, if you have this handy, do you have this handy? Because it might help for, do you have your thingy?
Yeah.
Because it's going to help.
That's true. Lower, raising the temperature.
Nope.
So requires less.
The thing about raising the temperature is it gives you more reactants, because raising the temperature makes your reactants have more energy. So they're more likely to go ahead and proceed to overcome that energy barrier. Yeah. Yep, so that's actually false. So does it, our rate law constant K's are Arrhenius constants times E raised to the negative EA over RT. So raising the temperature, if you think of it this way, to me, raising the temperature is not going to help your activation energy at all. It's still a barrier, but raising your temperature is going to give you, like I said, more reactants that have that energy to go ahead and proceed from reactants to products. Okay. Back to you, Daniel. I feel like I'm picking on you guys. If the concentrations of both reactants are doubled, then the rate will double. True or false? So we're going to their first order. I know my answer. It's like we're on a game show, right? Your answer. So you think it's true or false?
to say true and I want to say false.
Okay, why would you say
The reason
true?
I would say false is because it's like the same proportion. You know what I mean? In a way. So if you have like 1 to 1 and 2 to 2, but I feel like that's probably not it. So I feel like it's true because you just have more of each. So
I think you're thinking of stoichiometry. This doesn't have anything to do with stoichiometry. So,
yeah. Well, not exactly, but yes. But yeah, I see what you're saying. So,
yeah.
True.
True.
So it's just more mechanical, I guess. So then,
Well, yeah, and you're kind of thinking of mulling it over, which is good. I guess I would just go back to, do you see rate is equal to K times the mole concentration of each of the reactants? Raise their first power. So just mathematically, if I take, instead of the mole concentration, take 2 times, and 2 times that, what does my rate do? Increases by, yeah. So actually, this is false. And if instead of double, if we say 4 times or quadruple, then you'd be on track. And, this is one where it's a combination of thinking about what's happening on the molecular level and what rate is, and also kind of thinking mathematically, because we have this rate law expression. Okay. Okay. Back to you, Allison. Co-catalyst. We talked about catalysts. I think that might have been yesterday. What if you add a catalyst? Adding catalyst to the reaction will cause the initial rate of the reaction to increase. True or false? It's almost like by now you guys are gun shy. You're like, I'm just going to say opposite what I want to say.
Well, the initial rate is like A bracket 0 over A, so there's nothing happening.
No, that's the molar concentration. The initial molar concentration is A bracket 0. The rate is this guy right here. Rate.
Oh.
Yeah. So, what do you remember what catalysts do?
Is speed up the reaction. So I want to say true.
Yeah, they do. They speed up the reaction by allowing an alternate pathway with lower activation energy. So yes, that is true. Ding, 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 ding. It's like you have candy thrown at you when you get it right. Yes. Yes, it will speed it up. Okay. More with the true or false. This isn't associated with any specific thing. So what do you think, Daniel? Reactions are faster at higher temperatures because activation energies are lower. True or false?
this is making me think of what we just went over with it.
It should.
So that would mean that means true, right? I thought we marked false on that last one.
This one.
Is that just me? I put true.
Wait, it's saying the same thing, right? Just like the opposite way.
I can't remember.
I put
Rate.
true
This
for
one
some
said.
reason.
This one said raising the temperature lowers the activation energy, and we said false.
Right. Yeah. For some reason, I wrote down true. I don't know.
Yeah, and this is where I put this. If you think of the heart of the Arrhenius equation, here's activation energy. It is what it is. It's an energy barrier. Unless you add a catalyst, you get a different activation energy.
So that's the only thing that alters that.
Mm-hmm. Mm-hmm.
Okay. So I'm going to say false.
Yeah, that is false. And the reason a catalyst has different activation energy associated with the reaction is because you actually have a different script going on behind the scenes, a different set of elementary steps, different mechanism. Okay, so Allison, rates increase with increasing concentration of reactants because there are more collisions between reactant molecules. True or false? True. I'm liking true. Now we're on a roll. Yeah. Okay, Daniel? At higher temperatures, a larger fraction of molecules have enough energy to get over the activation energy barrier. Is that true or false?
Say true.
That would be true. Very good. Looks like you guys are solid on that one. And then back with the catalysts again. So what do you think, Allison? Catalyzed and uncatalyzed reactions have identical mechanisms. That is false. That is false. That's how catalysts work, because they have an alternate mechanism, different associated activation energies, lower activation energies. Okay, back to you, Daniel. Okay, so this is just a rearrangement where we have cyclopropane rearranging to form propene. And it happens to be first order. Okay. So for both of you, I'm gonna have a series of questions here in a minute. And each one of the questions is, as time unfolds, as time progresses, what happens to each of these? So it goes like this. This is assuming that your temperature is held constant. So Daniel, for instance, what happens to the molar concentration of that'd be the reactant as time progresses? Your choices are, what are they, increase, decrease, or stays the same?
Right.
Okay.
So we decrease.
It decreases. That's very good. It goes down. You got it. So Allison, over time, what happens to the molar concentration of the product? It increases. Yep, it goes up. Very good. So Daniel, over time, what happens to the concentration of the catalyst?
Remains the same, right?
Remains the same. You got it. Steady state. Remains the same. Back to you, Allison. What happens to your K, your rate law constant K?
It decreases, like half-life and stuff. Or no, it just stays the same.
Stays the same. Because there's nothing in here that's gonna, assuming the temperature stays the same. So that remains constant. Yep. Well, if K stays the same, why does the rate decrease over time?
Because there's less concentration.
Yep, the reason the rate goes down is because your reactant goes down. So I think maybe Daniel? So what happens, it's first order, so what happens to the reaction order over time? Stays the same, it's constant. Allison, what happens to the half-life, since it's first order, what happens to the half-life? I'm gonna look at that little sheet I gave you. So first order half-life. What did you find first? Does it increase, decrease, or stay the same? I think it stays the same. Yeah. Okay, by that,
Which way are you looking at?
this one. Stays the same. We are all in agreement. Okay, so here's one for you. Say you have something that you know is first order, and you're going to let it go for 5 half-life periods relative to what you started with. This is to you, Daniel. Relative to what you started with, how much will you have left? Let's look at the quiz. So if I start with, let's just say 1 mole per liter. At the end of 1 half-life, I'll have 1/2 of that. $164?
So you would multiply, like, yeah, okay, so it's
Mm-hmm. Yep. Very good. Okay, back to you, Allison, for 10 points. Okay, so I want, and this won't be just you, so we'll kind of go back and forth. Can you give relative rate? Well, first off, I'll give you a hint. We said that rate always has to be rate is rate is rate. And clear back when we first started this unit, we said that you can kind of normalize rate based upon what you track. If you take 1 over the stoichiometric coefficient and you track basically change in molar concentration of anything over versus time. I don't know if this is ringing any bells. I'll add one more thing to it, and then I'll kind of go back and forth between the two of you. If it is a reactant, you guys told me it's going to decrease, if that's what you're tracking, so you have to take it times -1. And if it's a product, it's going to increase, so you don't have to take it times -1. So clear as mud. So Allison, how could we come up with, I'm looking for the change in molar concentration of NO to change in time, but how do I go ahead and make that my rate?
U1 over 2 is,
Mm-hmm.
and then
This guy up here.
times -1.
Yep, yep. I can insert a negative right there, and that's it. That's it. -1/2 over -1/2 times the change in NO, change in time. That's the rate. So with that pattern, Daniel, what about the BR2?
-1.
Yep, I'm liking that. And then the last one, Allison, what about the tracking the NOBR?
-1/2.
You sure negative?
Oh, no.
1/2. Yep. And those will all be the same. Yep, yep, yep. Gotta have the same rate. Okay. Daniel, so we're switching it up. I kind of asked some leading questions, and we'll see if we want to kind of knock this out or just kind of at least set it up. So this is given, and we know that the rate of formation of O2, which is this guy, the rate of formation of O2 is, how do I want to ask this? Because I'm thinking through it. I'm going to unpack that for you if that's okay. I would unpack this information by saying the rate of change of O2. So I'd put delta change in molar concentration of O2 over change in time is, and then I would put 0.0015 moles per liter or molar per second. It's just kind of how I like to do it. Well, I guess I can then just go for the kill. So Daniel, what do you think? How would I express, so my goal here is, how would you express the change in molar concentration of O3 per time relative to the change in molar concentration of O2 per time?
Does this have to do with stoichiometry?
It does.
Okay. So, wait, I mean, so if you were to calculate, you can take like 0.0015 molarity.
And I probably would clean this up and kind of, I put moles per liter O2, yeah, and that might help you with your stoichiometry. And now what?
And then I would put on top, I would put 3 moles.
Yep.
Oh wait, it'd be 2 moles, right?
Oh, you're right. My bad.
3 moles of O2
Yeah, you were right. You're right.
Now we finish it up.
Yep. Close. So then, I guess, we talked about this is building, so this is in the rate. No, that would do it. It would be negative though. I think it would be negative.
Right, because it's reactive, right?
Yeah.
Let's take out my calculator.
Okay. Actually, 3 goes into that 5 times.
We got 0.001.
Thank you. And that would be moles per liter of O3 per second. Yep. Very good. Cool. Get you thinking. Thank you. Okay, back to you, Allison. Hydrolysis of sucrose, inserting water. Okay, so the observed, it's first order with regard to the reactant, sucrose. Oh, but notice that it's 0 order with regard to water. That's kind of fun. So it's first order. I'll I kind of might go back and forth between the two of you. So after 2.57 hours at this particular temperature, the concentration of the reactant has decreased from an initial concentration, so that would be your A0 of 0.0146 moles per liter, to now it's only 0.0132 moles per liter. We're supposed to find the value of the rate constant. Okay. So Allison, you've got a sheet in front of you, so let me kind of pencil in things, and I'm going to ask you which equation we should use. So this will be our T, our time. This one right here, the 0.0146 moles per liter, that's actually going to be our A0. And this would be our A. Okay. So we're looking for K. So based upon what you're going to have on the test and stuff, which one of these looks like first order that we should use to get down the road and answer K? Yep, I'm liking that. ln of A to A0 is equal to negative KT. I agree. So you guys want to work that, or? Okay.
So first get the K by itself.
Yep. Get the K by itself. So K is equal to negative 1 over T ln of A to A0. And then we plug in our values. I'm going to grab my good calculator. See what y'all come up with. You guys agree? It's like,
I don't know if I calculated.
Oh, so clear! No, it's good. You can use this one.
She has one.
fancy.
I'm small.
Doesn't
I can't even figure out how to turn it on.
It's to the right.
There's... She Walker, mister.
She Walker, mister.
You know how I work with calculators.
She's really exciting right now. I got 0.039. Woo! I like how she's like, this has nothing to do with your test. What?
How do you...
What? I don't even really.
Oh, whoa. Okay, how do you like go back up and slip that?
Like this? Just like answer? You can do like, kind of like this. Answer and whatever.
And then like, but there's one up here that is saved.
I don't know what this is.
Like,
I don't know.
yes,
This is what I do.
How can you do that?
This is what I would do. I would go and see.
Did you guys get the same number?
Okay.
We're still trying to.
I didn't have a calculator, so I figure out how to use his. And
You want to borrow one of these cheap ones? You can, but I don't know. $2 cheap ones. You can make a one.
Yeah, close parentheses. And then I would multiply that by. I got 0.0392.
0.029222618.
Yeah, that's what I got.
That's what I got. But shouldn't it be? Because I got like negative. I don't know. Did you get negative or positive?
Positive.
Oh, okay.
But maybe we did it wrong.
Wait, I didn't.
Because
I don't think I respelled it.
I get this is positive and this is positive. Wait. Oh yeah, I did it wrong. You're right. Okay, I did this. Okay, so yeah. Okay, so it is negative times negative gives you positive. Okay, huh? Very good. We're back. Okay. Since you.
Ask this question.
Uh-huh.
Go back real quick. Okay, when we rearranged that and we put the k on the other side of the equal sign and isolated it, what was the function that we did there?
We just divided both sides by t, by negative t. And so that's, to me, that's where this negative 1/t came from. So I think of it.
How come, I guess like when you're doing other math things, it's like you have to divide by ln, t by ln a stuff. But on here we didn't have.
Oh, okay.
Here we already had these, so we didn't have to break them out. We just kept it as an entity. Yep.
So we divided by negative t, and that made the k positive, and then that put 1/t. It's okay.
So the label is molarity per hour?
Well, since it's first order, units are going to be, let's see, first order we said it's per hour. Remember how that works?
Oh, so there's
Yeah.
now m. Oh, I just.
Yeah, K would have units of per hour. So in case Benny watches this, we got K is equal to 0.0 and give it 3 sig figs, 3, 9, 2, and that would be per hour. Yeah. Okay. All right. So here's another one. And so that was Allison. We'll pick on Daniel. We have hydrogen peroxide decomposing. It's first order. We are given the K. Let's see what sort of question we have. So question is, how long will it take for 15% of the sample? So we're after T. So question mark T. Okay, for 15% of the sample of the hydrogen peroxide to decompose. So I'm going to go ahead, before I ask you a question, I'm going to kind of give you a hint, because I had mentioned this in class. 15% will decompose, so 15% gone. So does this make sense that if that's what decomposes, that means you have 85% remaining? Do you guys buy that?
Yeah.
Okay, good. So again, I don't have a question yet for you, but I want to point out that 85% is actually, if I go ahead and take the ratio of A to A0, where A is the hydrogen peroxide concentration, do you buy this? Okay. So now, Daniel, which, and you have the sheet in front of you, which equation can we use to get to time? Well, we have K, and we have A over A0. We're trying to get to time.
This is the first order, right?
Uh-huh.
This doesn't have anything to do with the half-life equations, does it?
Nope. Don't overlook it.
Would be like the first equation to the left, like
Like this one?
ln, and then concentrate. Yes, that one.
But I don't have individual A and A zeros. But I do have a ratio of A to A0.
I guess then you could just use the one you just used, right?
I could just use the one we just used. I would do that too. ln of the ratio of A at time t to A0, which you started with, is equal to negative KT for first order reactants. And then how can we rearrange that? I should have asked Allison, but how can we rearrange this now, solving for T?
Divide by negative K.
Right. So T is equal to 1 over negative K times the ln of A to A0. I'll go ahead and jot down what we got. T is equal to 1 over negative 0.00106 per minute times the ln of 0.85. Sorry, this is pretty ugly. Kind of gone around and around. Well, there's a negative there. What'd you get, Daniel?
Not quite definitely.
Okay.
We got 0.00017227.
Would you take the natural log of 0.85
Yeah.
and divide that by 0.00106?
No.
Okay.
Okay, well, I thought, oh, I didn't take the inverse of that.
Okay.
I got 153.3.
Me too. So we'll go with 3 sig figs. So 153, and what would the units be, Daniel?
Let's see.
What units do we have? The things we multiply. So we have 1 over 0.00106 per minute, and this actually is unitless.
So just minutes. Okay.
Just minutes. Yep. Yep. Cool. All right, Allison. Are we getting close? Is this about the last one? No? Okay. Let's see. I'm just going to ask guided questions, I think, for this one. So, Allison, do you remember, and actually it's on here, I'm going to kind of point down here to, this is the Arrhenius equation. So do you remember what we plotted on the Arrhenius equation to get activation energy? This should be a hint. Y is equal to mx plus b. What's that?
Like this time and place that's part of it, but the LMK.
1 over temperature. Yep. So it's laid out y is equal to mx plus b. Yep. Negative slope. So I'll kind of go back and forth. Daniel, what would the slope be equal to then? Y is equal to mx plus b. Underneath here. What is m?
Negative activation energy.
Yep. You got it. And R is already given there. Very good. So, if I was given this information, I probably would make some columns, and I don't have this in the form of a question, but I would go with my 0.1 and my 0.2, and then knock out the, come out with my raw data, my Ks. Of course, I'm going to take the natural log of that. And my temperatures were given degrees Celsius. I'm going to have to convert that to Kelvin, and then I'm going to have to go ahead and take the inverse of Kelvin. So kind of bumping up against the clock. So, and then our slope, m is going to be delta y over delta x, so it'd be the change in the natural log of the Ks. Divided by the change in the difference in the inverse temperatures.
So that one will change in.
Did you find your calculator? Or is that Dan's calculator? Okay. I don't think we really have time to knock it out, but it'd be good review for you to do it on your own. Oh, we only have 2 more. Did you have a specific question, Allison? Or?
I had the.
Okay, we'll come back if we have time. Let's take a quick look at the next one. That's how you would lay it out. Did I ask a question for that one? Whose turn is it? Okay. Okay, Allison. So, what is the rate law? Well, I'll ask it 2 parts questions. First, Allison, what is the rate determining step? 1 or 2?
2.
It is 2. Very good. And so then, Allison, can you help me out and write, using molecularity, write the, the rate law expression for this elementary step? So this elementary step, so rate 2 is equal to what? K2 times molarity of the reactants. Yep. Okay, by the way, here's the overall reaction of interest down here. Okay. So we can't stop here, and actually, so Daniel, why is this rate law expression that I wrote down here, why is that not acceptable to be our overall rate law expression? I gave you a hint by putting an asterisk next to NOBR2.
Don't know.
NOBR2 is what we call an intermediate, so you can't stop there. So instead of asking in the form of a question, I'm going to kind of show you how we get rid of that. So our goal is to basically rate 2. We took the slow one, like Allison took the slow one, and we used molecularity, NOBR2 times NO, okay? But we got to get rid of that guy. So your instructions always are to turn to the fast one that goes before it. So in the fast one that goes before it, the rate in the forward direction is equal to the rate in the reverse direction. And the rate in the forward direction is equal to, I'm just reading it off of here, that first elementary step, NO, using molecularity, K1, NO, BR2, and the reverse direction would be K minus 1, and then the reactant, if I'm going backwards, would be NOBR. And then I'm trying to solve for this guy. So my molar concentration of NOBR is equal to my K1 over my K minus 1 times the molar concentration of NO times also the molar concentration of BR2. Now I have my intermediate. I'm going to go ahead and substitute that in for my rate 2. I'm going to substitute it in for my intermediate, and I'm going to rewrite rate 2, which was my rate determining elementary step, is equal to K2 times K1 over K minus 1, and then I bring down my, however I want to do it, NO times BR2. That was part of this guy right here. And then I have to, don't forget to bring my NO, which I had originally. So I go ahead and clean this up. I would say that I would expect the observed rate to look like this, where the rate is equal to the rate law constant K. I'm going to join my NOs, so it's going to be NO raised to the second power and BR2 raised to the first power, where actually K is actually behind the scenes equal to K2 times K1 divided by K minus 1. So that's how you do it. I'll post this out there. We got Dr. J's coming into the class. So if you're not here Friday for a lecture, you're probably going to want to be here Friday if you can. If you can't be here Friday, you're probably going to look at it because it kicks off Unit 3. And this is a class I wouldn't want to miss. I know people have to miss, but okay.